Hello, I am Andrew Borchardt,
And I am Andrew Adams.
and we're here today to talk to you about solar tracking for solar panels.
Solar tracking for solar panels. Often used for concentrated photovoltaics as these are required. However, they can also be used for statically mounted flat solar panels because the static mounting makes them inefficient. In 2009, it was estimated that 85% of static mounted commercial panels had the ability to add solar tracking. Solar tracking for flat panels is one of two different methods. The tip-tilt dual-axis tracker, or TTDAT, is a pole-mounted array, as seen on the left, which has a fixed cardinal orientation, and it is on two motors that control elevation in both the X and Y, creating the tip-tilt effect. The second tracker can support more weight and bigger panels. It is called the Azimuth Altitude Dual-Axis Tracker, or AADAT. It is one motor that controls the elevation and one motor that orients the panel so that it faces the correct cardinal direction, or azimuth, compared to the sun. Some of the basic equations we used to help work with our control started with just the power equation, where we have the voltage in the panel multiplied by the current generated by the panel to get our power. We are trying to maximize power at all points through the day with the solar panel by having the correct angle. This angle can be described as the angle of incidence seen on the elevation equation. This theta s angle of incidence is when zero means the solar panel is generating the maximum power. If this is zero, we can optimize this equation and have gamma s, the angle of elevation of the sun, plus beta, our angle of elevation of the panel, equal to pi over halves, so we can find the elevation of our panel.
This is a maximum power point tracking system. The maximum power point tracking system is a technique used commonly with photovoltaic solar systems to maximize power extraction under all conditions. The central problem addresses by MPPT is that the efficiency of power transfer from the solar cell depends on both the amount of sunlight falling on the solar panels and the electrical characteristics of the load. As the amount of sunlight varies, the load characteristic that gives the highest power transfer's efficiency changes, so that the efficiency of the system is optimized when the load characteristic changes to keep the power transfer at highest efficiency. This load characteristic is called the maximum power point, and MMPT is the process of finding this point and keeping the load characteristic there. MMPT devices are typically integrated into an electric power converter system that provides voltage or current conversion, filtering, and regulation for driving various loads, including power grids, batteries, or motors. In real-life application of solar panels, tracking systems, including dual-axis and single-axis, have advantages and disadvantages. Some advantages of tracking systems include they generate more electricity than their stationary counterparts due to increased direct exposure to solar rays. This increase can be as much as 10 to 25% depending on the geographic location of the tracking system. Solar trackers also generate more electricity in roughly the same amount of space needed for fixed tilt systems, making them ideal for optimizing land usage. With advancements in technology and reliability in electronics and mechanics, have drastically reduced long-term maintenance concerns for tracking systems. Some disadvantages of tracking system is their increased initial cost when installing the tracking system. Even with advancements in reliability, there is generally more maintenance required than a traditional fixed rack, though the quality of the solar tracker can play a role in how much and how often this maintenance is needed. Solar trackers are generally designed for climates with little to no snowmaking, making them a more viable solution in warmer climates. Fixed racking accommodations harsher environmental conditions more easily than tracking systems.
Error analysis. When using the random perturbations algorithm, there is a possibility in error that can result in inefficiencies. For small values of illumination, the current voltage characteristic is smooth. That leads to difficulties in determining the maximum power point, since changes in power are small compared to the voltage change. Another drawback of the algorithm of random perturbations is that it cannot pinpoint the moment of reaching maximum power point by the regulator. For the method of random perturbations, oscillations of working point around the maximum power point are typical, which reduces the efficiency of the algorithm. In case of the sudden change in illumination level, the algorithm can lead to erroneous results. The error can occur when the change in power due to changes in illumination exceeds the change in power caused by the algorithm.